So, next what I want to show you, so when you have a porous electrode, okay, how does the impedance vary? Within the domain of porous electrode, there are a lot of possibilities. What we are going to see is basically only one example, and after that, if time permits, we will go on to look at what happens when you have a film present on the surface. There are different models for it. There are simplified models which say the film is either insulating or conducting, and they can also assume that the film is dense or it is porous. Okay. The first case, which is given as porous electrodes, the first case what we are going to see is a conducting metal, but that is porous. Okay. If the conducting metal is just a solid metal, we know how to handle that. If it is a very thin film, so we have one metal on top of which you have another thin metal film, non-porous proper film, on top of which we have the solution, we can model that. If we have a film that is porous, we are going to see what it is. If we say the film is insulator, we can model that, we will see little later, and then if the film is insulator, but it is porous, we can model that also. Okay. For a film which is a clean insulator, it is pretty straightforward. For a film that is normally present in metals in solution, usually the film is not a clean dense film, it has defects, and film many times continues to form and dissolve. Okay. That model is little more complex. So, there are models for that, the description of those models we will see at the end of that. First, what we want to see is a case where you have an electrode. So, I try to draw this here. You see the dark blue lines here, they represent cylindrical pores. This is the front surface of the electrode that is exposed to the solution, and this is of course connected. These pores extend into the electrode, and the electrode is a conducting material, typically a metal. This front surface has an area. So, if I draw this here, I see lot of pores here, right. At the bottom of this, you will have an area, surface area for this. At the top, when there is no pore, those areas will also give rise to a particular area. The total area of the bottom of the pore and the non-porous area, it is going to be equal to the geometric area of this if you assume there is no pore. Okay. So, that is one area. Look at this pore, we are going to say it goes from x equal to 0 to x equal to L, and this has a radius of small r, and this side wall area is 2 pi r L, and if there are n number of pores, the side wall area is n 2 pi r L. So, we are going to start with the assumption that the side wall area is very large compared to the geometric area of this solid electrode. That means, we are neglecting the bottom area of the pore, we are neglecting the front area of the electrode where pores are not present. Full length meaning?
Full cylindrical length.
They travel up to length L. We are making some simplifications, right. In a porous electrode, you are not going to have necessarily cylindrical pores, you are not going to have all of them with same radius, and we are not going to have all of them placed evenly, positioned evenly, we are not going to have all of them with the same length, but we are making the assumption that they are identical pores. But other than that, they travel up to some distance, and beyond that it is solid electrode. So, if we have a electrode which is 5 millimeter diameter, 5 millimeter length, it is a small electrode. We assume the pores are very small in terms of the radius, and relative to the length of this it is still small, maybe it is half millimeter in length, okay. Maybe it is 1 micron in the pore diameter or pore radius. So, it is going to be many pores, very small pores, compared to the diameter of the electrode, the pore diameter is nothing. Compared to the length of the electrode, the pore length is nothing, very small, nothing means. So, we are going to say the surface area of a single pore is 2 pi r L, and if we take this as a pore, we should say 2 pi r L plus pi r square, because the bottom area also is part of the pore, but we are neglecting that. That is why I have crossed it out. So, what we want to do is find the impedance of a single pore, and then we can calculate the impedance of a number of pores and find the impedance of the electrode. We are going to make certain assumptions. Okay. There is no reaction here, there is only capacitance, double layer capacitance associated with the solid liquid interface. We are not applying any DC bias. Even if you apply DC bias, there is no DC current. If I take the electrode, if I take the pore, it has a double layer which can be represented by a capacitor. Now, this is the wall that is present. If there is no AC potential, you apply only DC potential, all that will happen is the double layer will get charged to some level because of the DC potential, and that is all. There will be a transient current for charging the double layer, but after that you will not have any DC current. Only when you apply an AC, the double layer will get charged and discharged. So, you will see an AC current, and since there is no species here which can react, we are not going to have ferroferry solution. So, if I apply DC, nothing will happen as long as I stay within the electrolyte breaking potential. As long as I stay within the water, if it is a water based solution, I should not go to a potential where water can break down. Okay. Now, if I apply a AC potential, some current will pass here. There is a solution resistance. Solution resistance is not negligible, we are going to say it is significant. Because of that, the potential here is going to be less. So, some potential comes, some of it is taken out here, it is going to be less potential, some of it is taken out, less potential, some of it is taken out, it is going to be less potential. So, potential will decrease with respect to distance, and we will find a way to account for that. In case this is a solid electrode, it is not porous. If I apply an AC, I will get a AC current which can be modeled using a solution resistance outside the electrode. From the reference electrode to this porous electrode is one solution resistance plus a simple double layer capacitor. That is all we need to describe this situation. If I plot this in a complex plane plot, high frequency, it will be close to the solution resistance. Just make up a number and say 10 ohm centimeter square. Capacitance will offer almost 0 resistance, because the capacitance is going to be giving us an impedance like this, and when omega tends to a large value or infinity, you are going to say that is going to give us 0, this is going to be our solution. And when we reduce the frequency, we are going to get an impedance from this, it is going to contribute only to the imaginary part, and then we are going to add the R solution. So, it is going to be a vertical line starting at R solution, and then it is going vertically up. For various frequencies, you are going to get various points. You can visualize this part, and correspondingly Bode plot, you can plot it and see. When you have pores here and solution is present inside the pore, and it is going to cause a decrease in the potential as we go inside. This will have an effect on the observed current here. Okay. So, this is just to reiterate that we neglect the front electrode surface area and actually the bottom of the pore also, and the solution conductivity we are going to denote that by rho. If we take unit surface area, then the impedance corresponding to the double layer is given by 1 by j omega CDL. So, what we want to do is take a small section here, okay. Potential will get, it will decrease here when we move from location x to x plus del x. we take any small section here, we are looking at a cylindrical surface, okay, and that is going to be I into R, because when we go here potential is decreasing, we are going to write it as I into R with a negative sign. R is given by conductivity multiplied by the length divided by the area. The relationship between conductivity and the resistance is how long is it. If it is longer, you are going to have more resistance. If the area is more, you are going to have less resistance. Okay. So, that is given by area here is for the cylinders, the block cylinder block which is containing the liquid. So, solution resistance causes a drop in potential, and that solution resistance for this small section cylinder is given by rho del x by pi r square. Now, if I want to find as I go in the length, what is the potential drop? dE by dx, it is going to be given by rho by pi r square I. So, I write here as rho del x by pi r square. So, I rearrange it and say del E by del x at the limit of del x going to 0, it is going to be written as dE by dx, and the remaining terms are rho by pi r square into I. We do not know what the I is yet.
Function with distance.
Yes, I is a function of distance. So, if you visualize this, you apply an AC potential. So, it is going to go with an amplitude. Okay. At the wall, current that is coming in, this potential is going to be large potential, or whatever we are giving, that is the maximum potential. It is going to oscillate like this at whatever frequency we are giving it. Little later what happens is some of the current is taken here, and the potential is decreasing here, because it offers a resistance, this small section offers a resistance. Remaining current is going to see a relatively smaller compared to this is going to be little smaller amplitude, and that will take up some current here. Then that means the potential oscillation here is going to have a even smaller amplitude, and that will take up little current. So, what happens is the current that is taken up is going to be higher here, and it is going to be lower as you go along. Sum of all these currents has to come from here. Okay. Now, if you want an analogy, think that you have a pipe, okay, and the pipe has pores. If you send in liquid with the particular pressure, of course, there DC is possible, okay, equivalent of DC is possible. Send in with the pressure, some will go here, some fluid will leak out of this, pressure will decrease here. Because of it, some more fluid will go out, but it will not go out at the same rate as in the beginning. Some more fluid will go, and likewise it will keep going, pressure will keep decreasing along this. The total fluid flow rate here under steady state condition should be equal to the integral or sum of the fluid flow rate at all these sections. This assumes the points or the holes are of similar size. I will not get even flow out of this when I go along this length. I will get higher flow rate and lower flow rate, higher flow rate in the beginning and lower flow rate at the outlet, but the net flow rate here is going to be enough to tell what is the total flow rate here. So, this is at any location, this I is equivalent to flow rate at any location. Of course, it is going to depend on x. Now, as we mentioned before, if we apply only DC potential, current will be 0. If current is 0, there is no pressure drop here, or there is no potential drop here. That equivalent is not there in the flow in a pipeline. So, if we have considered flow in a pipeline, that will be equal to having a redox reaction with present here. We are not considering this, we are saying there is no reaction. But when you apply AC, you will have an AC current here. So, AA capacitance will give you a current, and that is not 0, potential drop is also not 0. Now, if I take a small section and look at the cylindrical surface area, So, surface area here is the sidewall area. Okay. Impedance is going to be del E by del I. Okay. Impedance per unit area is given by this. If I want to look at the current, not current density, what I have to do is find this value del E by del I. Here it is E here is not the DC potential, it is actually E here is EAC, which is EAC 0 sin omega t, except this EAC is a function of location, EAC 0 is a function of location. In the beginning what we specify is EAC 0, as you go along the amplitude keeps decreasing. So, this phasor is what we mean by E here. That means, it is an AC with a particular frequency, but with varying magnitude, the magnitude varies as a function of location. This delta E, if it is a DC, it will tell E2 minus E1 if I say this is location 2 and this is location 1. Here what it means is, if I draw this, this is how the sinusoidal potential will go. As I go in, the amplitude will keep decreasing. Here this is EAC 0 at location 2 minus EAC 0 at location 1. That is the delta E here. This is not EAC. Earlier we would have taken del E is EAC and that is equal to EAC 0 sin omega t. Okay. That is not the del E that is used here, the notation is different, it has to be interpreted a little differently here. So, this del E is the dependence of the amplitude with respect to the location x. So, the current that is going here is related to the potential current density. Okay. So, here del I means the amount of current that goes in a small section here. So, if I integrate all the del I, I will get the total I. It is like the quantity of liquid that is flowing out of the porous pipe. So, in a small section here means through the surface area of 2 pi r del x, how much current is going. Okay. That is going to be given by potential by impedance. Now, if I shrink the del x to 0, at that limit I can write it as d I by dx. E is kept as E, remembering it is an AC potential. Z double layer or Z CDL, it is going to be 1 by j omega CDL. So, all that we see is the capacitance current here, except the AC potential's amplitude keeps decreasing, therefore, the current through the sidewall for a given sidewall area will keep decreasing as we go along. So, that is what is given here. d I by dx, as we go along it is going to be decreasing, therefore, it is negative. How much is the current? That depends on how much is the potential, how much is the frequency, diameter of this or radius of this pore, double layer capacitance. So, I have two equations, one is d by dx relating to the current, another is d I by dx relating to the potential. So, we take the d by dx and take a derivative with respect to x. You are going to get see what we want to do is find the current, find the impedance for this one pore. Okay. We want to find E by I. E here is the ACE and correspondingly I. In order to find E by I, we need to find E as it goes along the pore, it is changing. We know the E at the entrance, we know the pore diameter, we know the pore length, we know the conductivity, we know the double layer capacitance of the sidewall per unit area. From this we want to get an expression for the total current that is going in as a function of potential. So, we want to write E by I, remembering that E and I are vectors. So, we want to solve for E in terms, that is one you can solve for I, we will solve for E here. This you can rearrange and solve, correct. Rho is a constant, R is a constant, CDL is a constant, omega for a given frequency it is fixed number anyway, it is not dependent on x. Okay. So, you have an equation which goes like d square E by dx square minus m square E equal to 0. Where m square is a constant.
So these are the potential at x, right?
Yes.
So we are looking at it like this, like not along the length.
No, we are looking at along the length.
As in we are saying CDL is the capacitor of the pole wall.
Yes.
And we are saying the current that goes through will be the same because.
Okay. One assumption we make is potential at the center and potential along the radius, they are all the same. Potential decreases as you go along the length of the pore. It does not decrease as you go from the center to the edge of the pore. That is another way of saying the length is lot longer compared to the diameter of the pore. So, we will see numbers little later to indicate what is meant by lot longer. When we neglect the front area and the back of the pore area and then say this pore side wall area is much more significant than this, what numbers would give us this? You can do this yourself and see, but we will show examples. So, you are okay with this? We get solution in terms of exponential functions with m given by j omega 2 rho CDL by R. We need boundary conditions, right. One, at x equal to 0, E is actually E is 0 sin omega t, but I just want to find the maximum of the sin. That means, I want to find how the envelope of this sinusoidal current will go as I go along. That means, if I do not have any resistance here, it is just going to be a sinusoidal wave throughout this, whether it is high frequency, low frequency, it does not matter. This is going to be the envelope. Because the solution has resistance and it is going to be a sinusoidal wave, but bounded by an envelope which is decreasing with respect to distance. So, here I am going to just say E equal to EAC 0, remembering it is part of AC wave.
So resistance means we are talking about the
Solution resistance.
But when we reduce the distance delta x tends to 0, we have proved that whatever the impedance, it is because of the capacitance, not because of the solution.
See, the impedance at the side wall is because of the capacitance. Okay. Total impedance, it is going to be because of the resistance plus the side wall capacitance. Whatever current that is going through the resistor has to go through the capacitor. So, it is like saying the flow rate here, if I take a pipe, flow rate here, some of it is going to go here, some of it is going to go in the next section, some of it is going to go to the next section, but whatever comes here, that has to be split into all this. And if I take a small section here and there is a pressure drop even from center to edge, for example, that flow rate is going to be equal to the flow rate through the pore. So, whatever current is going through, there is a potential drop, but current that is going through, right, because of the potential drop, current will be less and less, because potential will be less and less as it goes along, but the current that is going through this resistance is going to be equal to the current that is going out. Meaning, if I take this, current that is going through this has to be equal to current that goes out plus current that comes here. This current, this may be some units, right, 10 units, out of which 1 unit goes here, 9 units come here. This maybe 0.8 goes here, 8.2 comes here. So, I am just taking into multiple discrete sections. So, solution resistance will play a role, but if I want to know the current here, all that I need to know is and the potential here. It is like saying I need to know the pressure here and the pressure here and the resistance offered by this hole. Outside pressure is uniform, inside pressure will keep decreasing. The resistance offered by this will be the same. If the pressure drop is less as you go along, the flow rate will become less, but we can't say this does not offer any resistance. If you want, we can also consider the case where there is a pressure drop here along with the pressure drop here. The net pressure drop across this is enough to tell us, and the resistance there is enough to tell us how much fluid will flow. Finally, the eye that coming here has to go out of all this. Okay, now I will give you maybe a slightly better analogy. You have a pipe which is porous. Okay. Now, if there is no pore there, I will give a pressure, pressure will be uniform everywhere and then stop, it is going to be static. If there are pores here, the pores will offer a resistance, but flow will happen. In addition, I can also say this pipe does offer a resistance. It is not that it does not offer any resistance. That means, if I open this and I don't have any pore here, I will have a pressure drop here, significant pressure drop. Now, imagine this situation, some flow rate occurs here because there is a pressure drop here. It offers lot of resistance, but not infinite resistance. That is why flow is occurring, but some pressure drop will also occur here, right. Accounting for that, pressure drop is occurring across this, pressure drop is occurring across this. If I want to look at the fluid flow here, I have to say whatever has gone out, the pressure drop, because of this distance there is a pressure drop. The total pressure drop here will tell how much is pressure here, and we can calculate this is going to be the flow rate because of this. Whatever fluid that is coming here still has to go out through this only, and when I want to calculate the flow rate here, I need to know the local pressure and the local pressure, that is all I need to know, and the resistance. Whether the pressure here is low because lot of fluid has flown, or whether it is a case where there is no porosity here, but there is a pressure drop. After this there is porosity. This also will give you a flow here, correct, but this case will be different from a case where you have porosity from the beginning. So, I can look at this section, this may be 1 meter, this may be 1 meter. I can say I will take this section and just cut this and put it here 1 meter here. This flow rate will be different compared to this flow rate. Does it make sense? Same pressure in, this will offer a pressure drop. As long as there is a flow, there is going to be pressure drop. This will cause a less flow rate compared to the same P in with no initial section. Now, I can have a combined one where from the beginning itself there is pore. This will offer pressure drop, it will offer some flow here, it will offer a pressure drop here. This pressure drop will keep varying because there is flow on the side. Okay. If you look at a straight pipe, same diameter, del P by del x, when I have opening only here, del P by del x will be a constant for Newtonian fluid. When I have flow around this, del P by del x will not be a constant. That is effectively what we are accounting here. I do not know whether it answered your question, but okay, at x equal to 0 the amplitude is maximum. Okay. At x equal to L it is blocked, therefore, d by dx is going to be 0, potential is not going to vary with distance.
Sir, but when there is a flow in a pipe, there is a pressure drop because of the length, and if there are some other pipes connecting side by side, then there is a further decrease in the pressure drop because of flow. But here we are considering only the resistance because of this direction.
No, we are also considering double layer capacitance.
No, when we say that we have either we have a solution resistance at the center and we have a CDL resistance at
the surface, at the surface.
Of the
Yes.
Right. But we are not considering both the things as simultaneously. When we have a flow in a pipe, we consider there is a resistance in this direction. If there are some other pipes,
we are considering them simultaneously. See, one of them, this tells, the first equation here tells as you go along how it varies with length, that solution resistance comes into play. Okay. We are denoting I, but we are recognizing that I is a variable, and that I takes into account the double layer capacitance. So, double layer capacitance and solution resistance are taken together. That is why we get the equation which has both rho and CDL together. And in fact, when we finally come to the expression, we will see the ratio of these two impedances will also be a dimensionless factor that comes into play. So, the impedance or admittance because of the double layer capacitance and the impedance offered by a solution filled in the cylinder of particular radius and particular length, you can calculate the impedance. The ratio of these two is giving you a dimensionless factor that will tell how the impedance of the entire pore structure will vary. So, this much we are okay. You have two boundary conditions. First boundary condition, you can put x equal to 0, it will become C1 plus C2, and that is equal to AC 0. Second boundary condition, you take the derivative and then substitute x equal to L. So, we are going to get m C1 e power ml, then minus m C2 e power minus ml. So, we have two equations and two unknown C1 and C2. So, the second equation tells us the relationship between C2 and C1. Substitute it into the first equation. You can write C1 as e power minus ml EAC 0 and C2 is going to be e power plus ml EAC 0 by correct. So, you can get E as a function of x. And that is going to look E as a function of x, because E is going to be e power minus ml plus mx substituting for C1 and C2, you can write it as hyperbolic cosine ml minus mx by hyperbolic cosine of ml. At x equal to 0, it is going to be 1. Well, the factor is going to be 1, of course, you are multiplying that by AC 0. As you go along, this is going to decrease. At x equal to L, it is going to be it is not going to be 0, cos h 0 is, it is going to decrease by a factor of cos h ml, that is all. Now, we want to find the current at x equal to 0, because that current is going to be distributed inside, right. So, in order to find the current, we take the derivative with respect to x and use the relationship that dE by dx is going to be minus rho pi r square I. dE by dx at x equal to 0. So, if you take the derivative, you are going to get m outside, and then cos h is going to give you minus sin h. X equal to 0, you are going to get tan h ml, and therefore, you can relate the current and potential we want to find the value of EAC 0 by I. I here is the current, not the current density. That means Z pore is the impedance written in ohms. I am sorry?
That's only at the entrance.
I at the entrance is going to be distributed throughout this, right. So, what we do is this, when we apply a AC potential, we measure the current, we measure the magnitude and phase of the current, and we take the ratio and say this is the impedance of this system. Okay. So, what is going to be the current at the entrance, that is all we are going to measure. That current gets distributed unevenly inside, that is okay, but what are we going to measure? What can we measure if we have an electrode of this pore structure? This is the current that we are going to measure, and this is the impedance we are going to see from the instrument. So, we want to predict that. We assume we know the impedance inside the pore, that is how we are getting the total impedance out of this. The impedance inside the pore is given by this resistance plus that capacitance, except that this resistance and capacitance are all differential quantities and we are integrating them. How much is the potential drop? That depends on what is the conductivity, what is the radius and what is the length of this, not the full length, but whatever length we are going up to. At that level, what is the impedance? That is what we have, what is the impedance or what is the potential there, we are calculating, and that is how we have come to this. We assume that we know the double layer capacitance on this pore wall. We assume of course that we know the radius, length and the conductivity. If you rearrange and get E by I, here I gave us EAC 0 by I, but essentially it is E by I would get a factor like this and I can rewrite it with capital lambda. Okay. I am going to write capital lambda equal to m square L square. I can write this as capital lambda as ml, but there is a real reason why we want to do this, because it gives you a dimensionless number. Okay. So, multiply and divide this by L, I will get rho L by pi r square, and this is going to give me tan h is going to give me cot h here, because I take the inverse, and basically derivation here whatever I am showing you is from the book by Lascia, or no, book by Lascia, and it is also available in the web, not the entire book, but the significant part of that as extensive introduction to AS. Now, this first part is denoted as capital R subscript omega p to say this is the resistance of the solution inside the pore. Look at this, you have a pore, consider this as a cylindrical block filled with a liquid of conductivity rho, length L, I am sorry, length is L, pi r square. So, this is the pure resistance offered by this pore, that is all, without worrying about the side wall double layer capacitance. What about the ml, or what about the capital lambda? If you instead of ml, if you take m square L square, okay, m square L square we can write it, m we know it is square root of j omega 2 rho CdL by r, right. So, m square is going to be just the same factor without the square root, L square we keep it as it is. I am going to rewrite that a little, I am going to keep j omega CdL on one side, 2 rho L square by r on the other side. I am just rearranging it, okay. And the blue colored factors I am going to call them as admittance of the double layer capacitance. Multiply by 2 pi r L or multiply by pi r, divide by pi r, and bring the 2 to that side. This will tell you this admittance for this area of 2 pi r L. The rho L by pi r square is the resistance or impedance. Okay. So, if this is the admittance, I can write this as ratio of admittances or ratio of impedances. double layer capacitance based admittance divided by solution resistance based admittance. This is the impedance. So, I can say this inverse of this is the admittance and I can bring it to the denominator. So, the factor m square L square is basically dimensionless admittance, capacitance based admittance versus just the pure solution resistance, that based admittance, and this is for one pore. If I take n pores in parallel, that net resistance is going to be given by Z pore by n. I have to add the admittances to get the net admittance and then invert it to get the net impedance. And then there is a solution resistance here, that is the R solution from the reference electrode to this porous electrode, there is some solution resistance. That is what I give by R solution there. We have accounted for the solution resistance inside this porous electrode in our expression for Z pore. So, I want to give you a couple of examples. So, I want to say there is 1 million pore or 2 million pore per square centimeter. Okay. Each pore is of 1 micron radius, it is pretty small, and 500 micron pore length. So, compared to the radius or diameter, the length is pretty large, it is 250 times diameter. Frequency I am going from 100 kilohertz to 10 hertz, we can go lower, but the scales become such that you can't see some of the patterns in this complex plane plot. So, I have not gone below 10 hertz, but it is easy to use the formula and plot it for any range. Double layer capacitance, we take it as 20 microfarad per centimeter square, which is a typical value. Solution resistance, here the conductivity we take it as 10 ohm centimeter. Okay. So, these are numbers made up which are sort of realistic numbers. Now, what is 10 power 6 pore per centimeter square? 1 centimeter length is going to be 10 power 4 micron. 10 power 3 micron is millimeter, 10 power 4 micron is centimeter, 10 power 8 micron square is going to be 1 centimeter square. So, if we take 10 micron by 10 micron area, that will contain a pore of 1 micron radius, 2 micron diameter. So, divide this into 10 sections, divide this into 10 sections. Take radius of one section here, that is how it is going to look like. Okay. So, roughly if I take this, I can take it as a square for just an approximate number. So, I get 2 by 2 out of 100. So, 96% is still covered by solid electrode, only 4% or little less than 4% is corresponding to the opening of the pore. That is what I would get if I take 1 micron radius in this 1 micron radius and 10 power 6. If you say 2 into 10 power 6, 2 million, it is going to have 2 such. So, it is going to cover 8% or 7% of the surface area. So, it still has lot of area left on the surface. The sidewall area corresponding to that, if I have million pore, it is going to be 31 centimeter square. The area of the top and bottom surface is of course 1 centimeter square, that is how we had taken this. So, compared to 31, we are neglecting 1, means we are leaving around 3%. So, you should have some feel for the numbers. You can't just put 1000 number of pores, 1 micron radius, and assume that the sidewall area there, because 1000 is a large number, you can't neglect the sidewall area in that case. I mean, you can't neglect the front and back area in that case. This case, you are justified to say I lose 3% of area, I am okay with that. Okay. If you plot the impedance in the complex plane plot, using this expression you can calculate and then plot it. In fact, this is not correct, it should be written as ohm, but that is all right. or because I see here what it means is we are taking the geometric area of this electrode, it is 1 centimeter square area, therefore, we are writing it as so many ohms centimeter square. Normally, when you take a porous electrode, all that you know is it is porous. If you get a pattern like this in a solution without any reaction, you would say this comes from a porous electrode, let me see if I can recalculate the diameter and length, or if I have some way of estimating the diameter using SEM on that, you will not get uniform diameter anyway, right. So, you will measure this pore diameter and then take an average and say this can be a representative diameter, okay, or representative radius. See if you can estimate the length. Length is again going to vary depending on where you cut it, even if you put in SEM, it is going to vary. So, you can say can I model this using this particular description, then you take an average length, you take the average radius and then see if it can model this. When you plot it initially, you will not know all these things, right. So, you will just plot it based on the geometric surface area. Now, if you look here, note this complex plane plot looks like this, that up to some level they are overlapping and maybe at the low frequency there is a difference, that is what it looks like. Put it in the Bode plot, you will see even at mid frequency there is a difference. Just because on the same path the points are moved, it is like saying I have one simple resistor, one simple reaction, solution resistance reaction, double layer capacitance changes in two cases. In the complex plane plot, all the points will just keep moving there, you may not see the difference. Bode plot, you will see the difference. Likewise, in this case, it is better to display that in Bode plot and show that when you have twice the number of pores, magnitude decreases, phase follows similar trend, but they are not identical. Couple of more minutes, I will leave you. Okay. If I take smaller radius, same number of pores, smaller radius, you expect naturally it will offer more impedance, it does offer more impedance. Pattern looks like going up, but look at this phase, it goes up, comes down and goes up. All that we had done is for a cylindrical pore, right. You can have pores of different geometries. So, there are equations, pores, cylindrical pore gives like this, different geometries, different grooves will give you different shapes here. You can also have a distribution of cylindrical pores of different diameter, different radii. You can derive for those. Okay. You can have variety of cases with reaction, okay. With diffusion inside. When you have reaction, species will A and B will react, and depending on which way the reaction is happening, you can have increase in concentration of A, decrease in concentration of B, or vice versa. Diffusion of that can become rate limiting, it becomes lot more complex. Many cases you have to make approximations, but it is possible to see how that will happen. Here all that we see is a introduction to porous electrodes. So, you get an idea that it is going to be quite different from what you would see for a solid electrode. Okay. We will continue with this other part tomorrow. Okay, we will stop here today.